Hello, Capstone teams. This is your lab coordinator, David, and I'm going to give a quick walkthrough of the Power Budget example document that I shared with your Capstone professors. So this is not a requirement. I don't think it's an explicit requirement, but the document itself in Excel should offer a nice template for you to start evaluating the power that you need for your battery, how much is consumed by each device, how to estimate the overall decisions you need for selecting wires and configuring your software, how to run your project for any larger than embedded system mechatronics assemblies. So let's just do a quick walkthrough. I won't explain everything, but I'll give an introduction. Basically, the first tab on this spreadsheet is talking about what are the goals that you should be considering when you're making your power budget. It kind of explains why you would want to make a power budget. And when you start answering all these questions for yourself, then you can discover a little bit more clearly what estimates and what level of detail you need to go into to actually serve your own purpose, whether that's for supporting your electrical designer or supporting the person that's making the report on the specifications, looking out for your final demo, etc. The example that's been used for this, document itself is from the CAST team that was taking the Scuttle robot and creating a COVID-related sanitizing machine and all the mechanical and electronics associated with that. And so their system included an extra battery, a couple of extra sensors, and an actuator, a motor to move an arm up and down, and some powerful ultraviolet lights. We won't get into the sensor here on the right. That's for sensing the ultraviolet output. So go through the goals and ask yourself what you need to know before you begin. Basically, it's starting a little bit more broad, like what is the peak power demand of your machine? And then it gets a little bit more detailed, such as what cable sizes are necessary. Some of these decisions are already made for you. You have to consider what your project includes and what are your constraints to decide which questions are really relevant. And this should be, when you input data, you should really have clear answers for those versus skipping them. Then we come down to what you're going to compute. You're computing estimates of the device's consumption individually. You're computing data that comes in from the outside, from like data sheets, and then estimates that you come up with on your own if you don't have the data sheets for every single thing or for your operating condition. You're going to consider logically how your estimates may be valid so that you don't run into trouble having a completely wrong power supply when you're ready to do your demo. And then the bottom section says, well, how will the above information impact your design decisions, such as selecting a battery? So the following tabs are actually tabulated data, and we're going to do the normal view. So data from electronics. We're basically just capturing the key metrics that come from each of the components, the electronics, sensors, etc., that are included in the project or are planned to be included. We have modifications to the Scuttle platform that include a LiDAR. We have the elements on a moving arm that include ultraviolet LEDs and the motor that moves it. We have the Scuttle base machine and the general power consumption of that. We look at how many of them are included, what is the voltage that they're operating at, and then essentially get the total power to know when they're all running full speed, then what's the power consumed. And if you ran everything at 100% duty cycle, what would be the power demanded? Then we looked a little bit closer and break it into assemblies to say, okay, here's the power of each of our modules. That might help your designer who's addressing one module and the other designer who's addressing another. Then we have the peak current. This is going to help you with other decisions in your in your design, such as wiring and connectors, sizing, and selection of a power supply if you have an adapter. Next section is runtime. Okay, so we want to start with our design criteria. Compare the project target with the available energy. This was driven essentially by battery size selection. How many milliamp hours do we need in our battery for a mobile machine to do such a task? So we can look at the desired runtime as a key input. Said, well, we want it to run for 2 hours. That's the invention we've been asked to make. What is the average power coming from the previous tab that we expect to be using during this runtime? And then how many amp hours will we need to support that based on the battery's nominal voltage? Then we come back to capacity criteria. How much energy is needed given this many amp hours and this many watts? Now we're talking about if you want to select your own battery, there's no battery included in the devices that you have brought into your project, and you have to choose that yourself. Okay, well, if this is the voltage, then this is how many amp hours we need. And then you can design a battery or put batteries in series, etc. Then we have robot modules grouped by actions. This table steers us towards having decisions on how we're going to run the robot. Well, sometimes we will have our actuator assembly operating, and it's doing that when it's moving the arm. It'll move the arm 25% of the time. This is a ballpark idea before you go too far into your project. Then we say the power of that movement is this much, because I'll have the motor is the only item running during that time. So now we've broken down the power in a different way that says different conditions based on the sequence that your robot or your machine is operating. That's very driven by the task of your machine. Okay. System power map. We have different power sources. There's only one power source that's driving the whole system, but if you look deeper, the converter, which pulls power from the battery and only feeds certain electronics, it has its own, it is a power source as well. And so it can deliver a certain number of amps, and there will be certain devices that are connected to the 24-volt output, not all of them. And so this table, or actually this whole page, is to help us understand and decide, do we have sufficient power at each power source, not just at the battery, at the overall. So here we have an example where we did a conditional formatting. We said, well, the converter is going to crank out, the converter needs 8 amps, but our first battery selected only can provide 6 amps, and so this value comes out to a negative number. It's the only one that's negative. It'll be yellow if it has a small margin relative to the others. And then we should make a note and decide what to do about it. And you can put your notes here if you want to organize your design process in the same way. Then we have power losses. This is going to be more filled out, but basically an example is the converter that gives us 24 volts. It loses a lot because boost converters lose a lot. If you get an expensive one, you could maybe get it 90% efficient. But the Amazon types, they're more closer to 80% efficient. Next tab. All right, power exclusions. This tab is only relevant for teams that found that, well, they have a cluster of elements that actually ought to be excluded from the power budget. Make it simpler, make it easier to evaluate, because, for example, on their sensing and indicating array, all of the power consuming devices are in milliamps. So there's two possibilities. One of them is you're looking at these LEDs and you're going to say, well, we'll just negate this from all our computations because it won't have an impact on the project. Or you can say that these devices are all pulling power from a specific source, such as the Raspberry Pi, and when the Raspberry Pi outputs to its 5 volt source at the USB ports, that has its own limitation. This table can remind you to go back into the data sheet of the Raspberry Pi and then check, well, how much current can I actually drive from that device itself, since it's doing the job of regulating at 5 volts. Actions, this is a place for you to just make your notes about how this will have an impact, maybe a discussion about why you estimated something is not too relevant and you've omitted it from your overall final presentation. Then justifications, this tab is, it's a pretty rough draft, but I included the examples of, this is a discussion that came from the Capstone team in fall of 2022, spring 2022, how they made their decisions about duty cycle. And there will be other estimations that you want to make, not just duty as indicated in this column. Then references also, these really are ultimately going to find their way into your final document if they're relevant. But during the design process, you might have a nice list of bookmarks that you should be sharing with your other team members. You might toss them out at the end, or you might realize that you continue coming back to them, and they're really driving the explanation for your overall power evaluation. So feel free to use this whole Excel spreadsheet. I strongly recommend thinking thoughtfully about this, and I think that thoughtfully about the questions, so that you can trim back your work overall and only deliver in your deliverables the information and the calculations that really matter. And then you can set aside everything else simply by justifying it if you've thought of it, or if you haven't thought of it and it's not on this list, maybe you're going to be okay without it. So hope that helps, and you can just talk to your professor if you need to get a copy of this Excel spreadsheet.